Think of a brand new industrial plant like a giant, high-pressure cardiovascular system. To keep the whole operation alive, a massive network of metal vessels and pipes has to continuously pump materials day and night. This diagram shows an exploded view of the core equipment making up that system. These metal shells face a brutal operating environment, dealing with extreme temperatures, massive internal pressure, and corrosive fluids tearing at the walls. Because of those intense forces, the margin for error is razor thin. If a single microscopic structural flaw makes it into the final assembly, the pressure will find it. And when it does, the result is a catastrophe for the entire plant. This illustration maps out the solution, a three-step engineering health plan. It's a journey that starts with material selection, moves through a diagnostic toolkit for testing, and finishes with a final pressure gate. This sequence is designed to ensure the system is ready for the forces it's about to face, long before a single drop of product is ever processed. Step 1 is material selection. You can think of this as choosing the exact right DNA for the plant. Engineers have to manipulate the base steel to maximize its physical toughness. Here, we see a microscopic comparison of steel grain structures. On the left is standard steel, with a coarse grain. On the right, the steel has been normalized. This process tightens the grains into a finer structure, significantly increasing the metal's ability to handle stress. This semicircular gauge tracks the carbon equivalent, or CE. It predicts how easily this steel can be welded without cracking. Pushing the needle into the red zone above 0.5 spikes manufacturing complexity, requiring expensive heating treatments before and after welding. This graph illustrates exactly why finding those material flaws early is so urgent, tracking the exponential cost of rework over time. A $1 fix at the raw plate stage balloons into an impossibly expensive repair or total failure if not caught before live operations begin. Securing the correct molecular foundation up front is the only proven way to prevent that kind of massive financial and operational friction during construction. Once the correct steel is selected, we enter Phase 2, stagwise non-destructive examination. These are continuous, medical-style checkups performed during assembly to find hidden defects without having to damage the metal. This comparison shows two tests acting like the dermatology of steel. On the left, a magnetic field pulls iron particles to outline a crack. On the right, a liquid dye creates a red bloom. Both methods map surface-level integrity, exposing flaws invisible to the eye. To look deeper, engineers use ultrasonic testing. As this diagram shows, it works like an industrial sonogram. A probe safely bounces high-frequency sound waves deep inside the metal to map internal flaws, though it does require a smooth, clean surface to work correctly. For the clearest internal view, we use radiography. This schematic shows the industrial X-ray process, shooting a radiation source through the pipe to capture internal anomalies on film. However, utilizing live radiation requires strict safety perimeters and facility evacuations to protect workers. This comparison chart marks how the four tests stack up across cost, flaw detection, and safety hazards. It reveals that every single method has a distinct limitation. Relying on just one of these tests creates fatal blind spots. True engineering assurance requires layering these tools together, step by step, to get a complete picture. Phase 3, the final gate. Before the plant goes live, we subject the completed assembly to extreme stress. Notice the orange markers on this diagram. These highlight stress razors, physical concentration points around joints where metal is most likely to fail under massive load. To test weak points safely, engineers use hydrostatic testing. The entire vessel is pressurized with water. Because water doesn't store energy, pressure drops instantly if it cracks. As the thermometer shows, water temperature must stay between 70 and 120 degrees to prevent fracturing. Contrast that with pneumatic testing, shown as a red, particle-filled vessel with an explosive hazard warning. It forces compressed gas inside. Because gas is highly compressible, it stores extreme potential energy. If it fails, that energy releases instantly, exploding like a bomb. This visual summarizes the process into 3 core requirements: being proactive with materials, checking quality at every stage, and refusing to compromise on safety during the final test. By treating steel like a patient, starting with the right genetics, running checkups, and applying a safe stress test, engineers create a blueprint of integrity. It is a meticulous process that protects both the financial investment and the human lives operating the plant.